Hello and welcome. Today we're going to talk about using some more ROM subroutines in our own assembly language code. Today we're going to cover printing strings and converting numbers to strings, and we're going to explore the string buffer. And we'll also talk about my strategy for figuring out how to use undocumented ROM subroutines by using the Unravelled book. And as a bonus, we're even going to use a documented ROM subroutine. Which one? You'll have to watch to find out. So I'm going to show you what this code does first, and then we're going to look at the code and talk about how I figured out how to call the routines that I was calling. This is mainly an exercise in converting floating point numbers as represented in the accumulator to strings that I could then print. So it starts off printing 10. I hit a key on the keyboard, moves on to 256. I hit another keyboard, we're at 0, now we're at negative 10, negative 256, negative 256.25, and then that number. These are just test numbers that were hard-coded into the code. But the idea is every time I hit the spacebar or any key, it'll cycle through the different tests, clear the screen, print the test, and then repeat again. And here's the test data. So each row consists of the 6 bytes that need to be stored in the floating point accumulator. And then in the comment, I just say what it's supposed to be. So I was just testing the ability to convert to a string an integer, a 0 integer, a negative integer, and then integers with a decimal after them. So not integers really, but rational numbers. So routine number 1, clear screen. So the Unravelled book tells me exactly where it's located. It tells me what it does, what registers it upsets. There's pretty much nothing for me to do to set up for this. But I don't take this at face value. I also look at examples of how it gets called. So I search through for A928 just to see what happens around it. And actually there really isn't too much going on around it. So each time I run into it, I just see something like this. It just jumps to a subroutine, and there isn't much to set it up first. The next thing to check is how to print a string. So assuming I already have a string, how do I send it to console out? We've got a routine right here to do that. And again, it looks like it's pretty straightforward. The X has to point to the string, and then you call this, and it prints it. But this is a case where actually looking to see how it gets used was quite valuable. So here the routine is called to print the color basic copyright message. And one thing I notice is that X is loaded with an address -1. Why did they subtract 1? Let's actually take a look at where that is stored, A147. So A147 is just the string color basic 1.2. There isn't like anything leading it that it needs to backspace over. So it's pointing right here, and for whatever reason, they're subtracting 1 before they print it. Maybe that's a fluke. Maybe it doesn't do it everywhere. Where else does that string printing routine get called? Well, here it's called to print OK. And again, they're subtracting 1 first. Here it gets called to print, I guess, Microsoft. And again, they're subtracting 1. What the heck? What's going on? Maybe we'll find out if we see what that routine is actually doing. So here's the routine. And the very first thing it does is it initializes the terminators. So this tells it when to stop scanning the string of characters, when to know that the string is done. And this is one of the terminators. In fact, I guess this is all the terminators, the double quote. And if you continue on, you'll see they deliberately add 1 to X before they start doing stuff. And I think it's because normally this is called when X points at the double quote. And so in order to print a string, it will have to go beyond that double quote and it will stop before it gets to the next double quote. So this routine is mostly used to print like literal strings with those literal terminators on either end. So if I'm going to use this myself, or if other parts of BASIC are going to use it, they need to know to backspace 1 so it will know to skip forward. So it kind of like fakes there being a double quote beforehand. Next up is POLCAT, which you can call and it will return what key is pressed, if any key is pressed, or just 0 if nothing is pressed. This is one of the rare examples of a routine that's actually documented by Tandy Radio Shack. As such, POLCAT does not actually point, this symbol does not actually point to the routine. It points to 2 bytes in memory that store the address of the routine. That way, if in future versions of the ROM they need to move things around, they can move it wherever they want, but POLCAT stays here at 8000. So POLCAT at 8000 will just have 2 bytes that can get changed as needed to point to the actual routine. In the Unravelled book, they call the actual routine key in. And key in simply scans for a key depression, and it zeroes out the 0, I should say it sets the 0 flag if nothing is down, which is kind of like asking if there's something and it returns null. Otherwise, you will find the ASCII value in the A accumulator if something is depressed. So not much really to do there. In fact, it doesn't even disturb much. It only disturbs the 1 register that it needs for the return value. So this should be fairly simple to call. But just to double check, how do other people call it? This is a great example. They just branch to the subroutine and then they branch if equal to something else. So this is really the exact kind of thing I want to do. If nothing is down, then go back up and loop. Loop, 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 loop. And in fact, in this case, they're blinking a cursor while they're looping. I don't need to do that. So I'm just going to have a couple lines that go to POLCAT, and if it's equal, meaning the 0 bit is set, then go back up and repeat. And only if something is pressed do we break out. So let's take a quick look at how I'm calling those routines. This is after the part where I've gotten my string and X is pointing to the string. So the first thing I do, and I don't know if I need to do this, but the device number, that's a well-known location in RAM that says which device you're printing to. And when this is 0, that means you're printing to the screen device, as opposed to, say, a cassette or a floppy disk. I save my X because X is pointing where I need it. I do that around my call to clear screen. And then I restore my X. And since X is pointing to the string I want to print, I need to subtract 1, as we learned, to kind of fake that it's now pointing to the supposed double quote, because when I call the print string routine, it's going to advance 1, ignoring wherever it's pointing. And POLCAT is called right here. So after that's all printed, I just have this simple 2-line loop. I jump to POLCAT, and then if EQ, if the 0 bit is set, I go back to call POLCAT again. Just keep on doing it until we can break out. You'll notice I'm putting square brackets around this because, again, there's that extra level of indirection. POLCAT, that symbol, is not where POLCAT is stored. The POLCAT symbol is where the address of the actual routine is stored. So we have to look inside here to get that address so we can then jump to that address, whatever is stored there. So that brings us to the star of the show, BDD9. This is what will take a floating point as stored in the floating point accumulator bytes and transform it into an ASCII string. And this is pretty much all they tell us. It converts the floating point number in there into an ASCII string in the string buffer. The string buffer. You might recall that in my last video I was slightly obsessed with looking at the string buffer, seeing where it is and what it looks like and what it does. This is why I wanted to understand better what this string buffer is all about. So the string buffer is an area of memory starting at 03D7, and it's 41 bytes long. A very strange length, but that's what it is. It's just memory sitting around for use for various scratch operations, but I think mainly just for conversions between floating points and string. The stir dollar function in BASIC does something very much like what I want to do. It will take its parameter and convert it to a string. So I wanted to see how it uses the string buffer and how it calls the routine. And it actually doesn't call the routine, it calls like the next instruction into the routine. And beforehand it does this kind of curious thing. It loads U with strbuff plus 2. So it points you 2 bytes into the buffer. In the routine, BDDC starts here, and curiously, the instruction that we skipped loads u with strbuff plus 3. So according to the Unravelled book, this is, quote, the routine. This is the one that they chose to pull out and list as the routine that converts floating point to string. But $$ calls one thing into it, and instead of loading u with strbuff 3, it loads u with strbuff 2. So I did a little bit of debugging, and it looks to me like what's going on is wherever u is pointing, that's going to determine where the string gets converted to. And it also has something to do with whether the string gets stored in string space or just in the buffer itself. In fact, there's another comment later on, shortly after the $$ function gets started, that talks about whether the start of the string comes at strbuff plus 2 or after. So something like strings that start at strbuff 2 or earlier get also stored in the string space, but if they start at strbuff plus 3, they don't. I don't really know what this is all about, and I did not have that much interest to look into it. But the main thing I wanted to understand is how do I prepare to call BDD9? And apparently I could skip this and just directly call BDD9, and then I would expect my string would be stored at strbuff plus 3. So let's see what the debugger has to say. So we're in the debugger just about to run that routine to convert BDD9, and I have the memory window open to the very beginning of the string buffer, 3D7. So right now it's all zeroed out. So I'm going to step over this, and we're going to see what happens in the memory window. So what we were converting was 10, and if I take a look, we are skipping past this beginning, so this would be strbuff plus 0, strbuff plus 1, strbuff plus 2, strbuff plus 3. So we're right here at the 20, hex 20, with it, which is the space, and then we're looking at, you can actually see here, 1, 0, and then a null terminator. So although it looks like a dot here, it's just a null terminator. But it starts at strbuff plus 3. So I'm going to just go, and the next thing that we convert should be 256. So keep your eyes here. We're going to step. And again, 0, 1, 2, 3. There's our leading space. So let's do this a couple more times. Let's get to the negative numbers. And here we are at -10. And again, we're at strbuff plus 0, 1, 2, starting at 3. So that's where our negative comes in. There's no leading space. You probably remember from BASIC that BASIC always loves to print numbers with the leading space unless it's negative, and then that leading space gets filled in with the negative sign. And that's what's happening right here. It's happening right at that conversion routine. And just for fun, let's take a look at what happens when there's actually a decimal point. We're starting at strbuff plus 3. We have our -256, and then 2e is our decimal point, and then we have our 25, and then a null terminator, and that's the end. So this is telling me that if I just call BDD9 and let it set u to be strbuff plus 3, then strbuff plus 3 is where I go to fetch my string, and I just keep reading until I get to that 0 byte, and I know I'm at the end. So now we're ready to scan through the final code. So just a bunch of symbols up top. The main loop I can actually fit all in one screen, even with this very large font size. So we start off having y point to our test entries. So this is our table of test entries, and y will be pointing starting at the very beginning. And we're going to use x to point to the floating point accumulator. And so we have a loop right here, which continually compares our input pointer, y, with the end of the table, and we break out if it's bigger or equal. Otherwise, inside the loop, we call our routine that does everything, which kind of leaves nothing left for this loop to do. In fact, this routine also advances y to the next entry, which is how I'm able to continually compare at the top of the loop. And then all we do is we wait until the user clicks a key on the keyboard, and then we go back up to the top to close the loop. So all that really matters is what's happening here, and run test. So run test uses y to point to the source as it was before. That's the test input table. X points to the destination, which it was already, which is pointing to the floating point accumulators. Then we use A and B to help with the copy. So you've seen this in previous videos, or at least a version of this. All this is doing is copying from y to x. And I'm just annotating which bytes of the floating point accumulator are getting copied. And then the remaining 3 pieces of the floating point accumulator that I'm not using at all, that relate to strings somehow, I'm just zeroing them out, and that's all that copy is doing. So now x is primed and ready for the conversion. So I do the conversion. That's it. That's all the prep I needed to do. So long as so long as the floating point accumulator has what I need, this routine does what I need, and it puts the answer in strbuff. But really, it puts the answer in strbuff plus 3, as we talked about. And then it's time to print, which you've seen. We clear out the device number, so we're going to the screen. We save our X, and then we call clear screen. X needs to backspace 1 to kind of simulate that there's a double quote there. And then the print routine is ready to go with X pointing just before where the string actually starts. And then we're done. We return. That's the whole thing. So for those of you who have stuck with me this long, a little bit of a treat. I'm going to run this, but I'm going to use my magic pokes so you get to see the string buffer instead of seeing the screen. First, we're going to do the ROM to RAM utilities, since we're going to be poking to the ROM. Oi! That lets us know we're all set up to go. And then we're going to load our conversion program while I can still see the screen. And then I'm going to do the pokes, which I stored away in a basic program. Those are the pokes. Run the pokes. Now we're looking, string buffer starts like right around here. And let's exec, exec. Oh, you can even see the line buffer there. Boom. So it's done the conversion, and here we are in the string buffer looking at 10, 256. So this is our leading space. These are a few nulls, I think. 0, negative numbers, negative with the decimal point. Not negative, but still with the decimal point. It does not get better than this, folks. And that was it. That was all I have. Now, every time I hit space, now I'm like going into the line buffer. Oh my gosh, I could play with this forever. Thank you for joining me on this journey. The journey is not over. We're going to do something with this. There's a reason I wanted to do this conversion. And in future videos, we're going to start to see what is going on in my mind.